Okay, so this is going to be the answer key for the 2016 addendum, questions 89 through 100 for the final. So make sure you have your periodic table, have your formulas sheet. So let's start going through these. All right, starting with 89. Which intermolecular forces, IMFs, are present in a sample containing the following molecules? I should have emphasized that these are like 5 or 6 separate samples. So when I have CO2, well, we've talked about this a lot. If you just recognize CO2 as being nonpolar, you'll realize the answer is just London dispersion forces. Remember the 3 kinds of intermolecular forces. The first one is London dispersion. That's the one that everything has. It's that sort of induced temporary dipole where just by having protons and electrons, by moving towards one another, they'll temporarily induce a slight charge on one side. The second kind is polar dipole-dipole. That is a type of intermolecular force that's present in polar molecules, CO2 not being polar. And the third type is hydrogen bonds, and really that's just a special type of dipole-dipole force present when hydrogen is bonded to one of 3 elements, nitrogen, oxygen, or fluorine. So we need to see whether CO2 is nonpolar or not. So let's quickly write out the Lewis structure. So our carbon is always going to be our central atom here. So it's going to look like this. And now we have to add up how many total valence electrons we have here. So carbon is going to contribute 4, and each oxygen is going to contribute 6. So that's going to be 12 here. So total is 16. Now we distribute them around all of our atoms and see what adjustments we have to make. So let's do pairs around all of these. And add them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So you should have either the right number or too many. In this case, we have too many, so clearly they can't be distributed this way. We don't have enough electrons. So anytime we turn 2 pairs into one double bond, we are cutting down on 2. So because I have 20 and I want to go down to 16, we're going to cut it down by 4 by making 2 double bonds. So clearly we can knock off some of these pairs like this, and like this, and we're going to make double bonds here. Actually, I took too many, or I took the wrong ones away. I should have taken off the carbon. So I'll pull 2 off the carbon. I'll pull another 2 off the carbon here. So that's my CO2. Okay, let's just recount. 2, 4, 6, 8, 10, 12, 14, 16. So this is the proper Lewis structure for CO2, and because it goes in a nice straight line, that's going to be linear. Because the electronegativity difference is pulling equally on either direction, we're going to consider CO2 to be nonpolar. So therefore, the only type of IMF is London dispersion forces. Okay. Let's do the next one. Still on 89. H2O. So you should have this one pretty much memorized what it's going to look like. So we're going to have our O as our central with 2 H's. Okay. Now we should know that it's kind of off to the side like this, but just for the sake of drawing, let's make it go across. Okay. So we're going to have 2 lone pairs on the oxygen. This accounts for all of our electrons here. So you might think this is linear. But in reality, if you look at this 3-dimensionally, it's not going to be linear because it's not going to arrange itself in that cross pattern. It's going to arrange itself in a tetrahedron or tetrahedral shape where it kind of looks like this with the O in the middle. It's going to have 2 lone pairs on the top, and then we have sort of 3 legs coming off the bottom. This is kind of how we show 3 dimensions. And we have 1H, 1H, and another lone pair. So really, the 2 H's sort of stick off to the side. So we have the oxygen with the hydrogen, and lone pairs like this. Okay, so that's just my Lewis structure, but talking about the type of IMFs, this is definitely going to be polar. So we're going to have dipole-dipole forces. We're also going to have London dispersion forces because everything has London dispersion forces. And will this have hydrogen bonds? Yes, it will. That's why water has such very unique characteristics. It's the fact that these hydrogen bonds are here. They give it surface tension. They give it cohesion, adhesion. They give it capillary reaction. This is the reason water has such a high boiling point compared to other really small covalent molecules. I mean, if you look at it, pretty much anything else, Ch4, CO2, Cl2, H2, F2, these are all gases at room temperature. So why is H2O able to stay a liquid at room temperature? That's because of these hydrogen bonds, strong IMFs. Okay, xenon, Xe. This is just a lone element here, noble gas. So the only IMF present is going to be London dispersion forces. You can't have dipole-dipole, you can't have hydrogen bonds. So just London dispersion forces. PCl3. Hopefully this is one you can quickly remember from class. If not, we're going to have to draw the Lewis structure to see what kind of polarity we have. I mean, first, we can always tell it's going to have London dispersion forces because everything has London dispersion forces. Okay? The central atom is going to be my phosphorus. And we're going to have chlorine, chlorine, chlorine. And let's add up the total number of valence electrons. Phosphorus has 5, chlorine has 7 each for a total of 21. So that gives us 26 total valence electrons that we have to distribute. Let's put electrons on each of our lone pairs, I should say, on each of our atoms. Don't forget the phosphorus. And now we add them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 matches 26, we're good. No double bonds, no triple bonds, anything like that. Okay, so in terms of polarity, you might think, well, maybe the 3 chlorines are going to arrange themselves in this really nice pattern, which would technically give no polarity because it would be symmetrical. But they don't because there's a lone pair that throws them off. So this is going to arrange itself in a trigonal pyramidal shape, where we have the phosphorus with the lone pair on the top, and then we're going to have 3 chlorines off the bottom, like that. So, I should say Cl. Now, because it's arranged in this pattern, we are going to get polarity, where the phosphorus is going to be, I guess, positive, because chlorine is very electronegative, so these 3 chlorines are going to really hog those valence electrons, giving partial negative sides down here, partial positive side up here. So therefore, will it have London dispersion forces? Yes, everything does. Will it have dipole-dipole forces? Yes, it will, because it's a polar molecule. Will it have hydrogen bonds? No, because there's no hydrogen bonded to NO or F. All right, almost done with 89 here. Ch4 methane, or carbon tetrahydride. Carbon with 4 hydrogens. 2, 3, 4. This is going to account for all our valence electrons, and this is going to be a tetrahedral shape. 3-dimensionally, it's going to be 1 sticking off the top and then sort of 3 angled out on the bottom, like a tripod. Tetrahedron shape means each of these are pulling in perfectly opposite directions with the same strength, so therefore this is going to be nonpolar. So let's go over the forces. Are there going to be London dispersion forces? Yes, everything has London dispersion forces. Are there going to be dipole-dipole forces? No, because this is nonpolar. Are there going to be hydrogen bonds? No. And a lot of people think, well, look, there's 4 hydrogen bonds right here. But those aren't considered hydrogen bonds because it's not bonded to an NO or F. And the real reason for that has to do with electronegativity. The electronegativity difference here is about 0.4. Because just thinking off the top of my head, hydrogen I believe is 2.1. Carbon I believe is 2.5. So these are like, it'd be like if 2 really weak people were trying to pull something apart. There's not that much of a difference. I mean, if you stuck something like a fluorine in the middle of this, which you can't have 4 of these off of fluorine, but if you did theoretically, the fluorine would hog all those electrons and it would be very, very polar, but not this. Okay, so the answer is just London dispersion forces. All right. 90. Why does NH3 have a higher boiling point than NF3? The dot structures are going to look like this. Just do the lone pairs. Like this. Okay, the answer is they are very similar here. And in fact, this one has more mass, so you might think generally more mass, higher boiling point, but it's not. And it's because it's a type of IMFs. These both have London dispersion forces, because everything does. These both have dipole-dipole forces because they're both trigonal pyramidal, in that there's a lone pair on the top kind of pushes those three down. So it's the same so far, but here's the key difference. NH has hydrogen bonds. NF, no hydrogen bonds. So this is definitely going to be stronger because of the hydrogen bonds, which gives it a higher boiling point. 91. Categorize the following bonds as ionic, polar covalent, or non-polar covalent. Use an electronegativity chart online or in your notes to find the answer. So I don't have mine with me, so I'm just going to run through my answer key based on what I believe these are going to be. CH, that would be 2.5 minus 2.1, which gives 0.4. So technically that is polar covalent, but it's right sort of at the border. So it is often called nonpolar, but that's going to be, according to our category, polar covalent. NO, that's also going to be polar covalent. I believe that's 3.5 minus 3.0, so 0.5. MGS, I believe that on our category it comes out as polar covalent, although we know that to be ionic. Again, it's not like a one set sort of thing. There's always a little bit of a range to it, but according to our category, that would be polar covalent. CLCl, definitely going to be non-polar covalent. Anytime two things are bonded, the difference in electronegativity is going to be 0, which makes it perfectly nonpolar. And finally, HF. According to our measurement, I believe that's a 1.9 difference, which makes it ionic, though in reality it acts more like a covalent bond. Okay, 90. Oh, did I read the wrong one here? I did. I skipped one. Hopefully you caught that. That was 92. Let's go back to 91. 91 says, why does argon, Ar, have a higher boiling point than Ne? This just comes down to mass. If they have identical IMFs in terms of categories, then the higher the mass, generally that's going to have the higher boiling point. So neon is atomic number 10, atomic mass of 20.18. Argon, number 18, atomic mass about 39.95. So because argon's the heavier element, it's going to have more protons and neutrons, but also more protons and electrons, which creates that stronger London dispersion force. Okay, the more protons and electrons, the bigger that temporary dipole can be, and the stronger it's going to be. So that's why argon's going to have the highest boiling point. Okay, so we got through those. Let's look at 93 now. Two solutions are mixed. Silver nitrate reacts with sodium chloride. Write the total ionic equation, net ionic equation, and identify the spectator ions. All right, so let's start with the total ionic equation. Really, we got to start with our balanced equation, I should say here. So we're going to have silver nitrate. Because I told you it's a solution, it's aqueous. That's going to react with sodium chloride, which is aqueous. And so let's see, the silver is going to bond with the chlorine for AgCl, and that is a solid according to our solubility table, plus NaNO3, which is definitely going to be aqueous according to our solubility table. So here's going to be the total ionic equation. We're going to break all the ions up. We're going to keep all the coefficients, which in this case they're all just ones. And we're going to include charges on ions. We're going to include state symbols. Anytime something's aqueous, it's just going to break up into two aqueous ions. So AgNO3 aqueous really means Ag plus aqueous plus NO3 minus aqueous plus NaCl aqueous is just Na plus aqueous plus Cl minus aqueous. And really, this is a better way of representing it, because when I have AgNO3 aqueous, I don't really have silver nitrate. When I have NaCl aqueous, I don't really have sodium chloride. I have a mix. I have water that contains a mixture of ions floating around. So I really just mix 4 ions together. Now AgCl solid. Solids are going to stay together. AgCl solid. Okay? plus NaNO3 aqueous. So Na plus aqueous plus NO3 aqueous, and that's a minus, just like that. Okay, so that's the total ionic equation. The net ionic equation is just the things that are going to change, or in other words, you're going to take out your spectator ions. So the only thing I form here is AgCl solid. So this is just going to end up being Ag plus aqueous plus Cl minus aqueous yields AgCl solid. That's my net ionic equation because I removed everything that doesn't really do anything. Notice the NO3 minus and the NO3 minus are aqueous before, aqueous after. Same with the Na plus. They do nothing. That's your net ionic equation, and I think I asked for the spectator ions. Yep. So the spectator ions are just Na plus and NO3 minus nitrate. Okay. 94. Convert 63 liters into cubic meters. All right, so I'm going to take a volume unit or a liquid volume unit and convert it into a cubic length unit. My conversion factor to do this is going to be 1 centimeter cubed equals 1 milliliter. That's something we focused on early on in the year. So I'm going to need to take my liters down into milliliters. So this is going to be times 1,000 milliliters per liter. Cancel, cancel. That gets me milliliters. And now since 1 centimeter cubed equals 1 milliliter, I can go like this. Cancel, cancel. Now I have centimeters cubed. I want to get this into, where am I looking? Meters cubed. So I know 1 meter is 100 centimeters. So I'm going to go 1 meter over 100 centimeters. By the way, the way I know which one to put on top is I look at my units. If I want to get meters, I'm going to go centimeters on the top, centimeters on the bottom. Now what you can do is cube this, but then you got to remember to cube this. So what I always prefer to do is just rewrite it twice more. And check our units. Centimeter cubed does not cancel all the way with centimeters, but if I have centimeter, 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 now it's going to cancel centimeter cubed. And what unit am I left with? Meter, meter, meter. That's meters cubed. Okay, so you work out the math on this one. What are we on? 94 here. It equals 0.063 liters. And that's with 2 sig figs as it should be. Alright. 95. Write the orbital diagram, which is up and down arrows for these elements. Fluorine. Looking at the periodic table, I can kind of predict where it's going to go. I'm looking at 1s2, 2s2, 2p5. So 1s, 1 up, 1 down. 2s, 1 up, 1 down. 2p, let's do all 3 of those. And now we're going to fill them in the appropriate order. 1, 2, 3. And now that we have the 3 lone ones filled, we can go like this. Okay? That's the correct way for fluorine. For calcium, 1s2, 2s2, 2p is going to be filled, because I can look ahead and I'm going to see it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now look, I know this is going to be filled, so you can just go up, down, up, down, up, down, but I like to always practice by going up, 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 down, down, down. 3s is going to be filled, 3p, up, 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 down, down, down. And finally 4s, we're going to go 1 up and 1 down. So that is filled. Finally silver, Ag. This is going to take a little bit of work here. So looking at my periodic table, I'm just going to keep tracing all the way down. So I'm looking at 1s2, 2s, let me aim at the periodic table there. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now I have these. This is 3d10, 4p6, 5s2, 4d. Remember, with the d, you drop one number down. So it's 4d, and look, I can see silver here. It's going to end in those 4d's. So I'm going to say 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to end at 4d9. That's what I know. So let's draw it out. 1s is filled. 2s is filled. 2p is going to be filled. 3s filled. 3p is filled. I broke my own rule there. I should have gone 1, 1, 1. 4s is filled. Now before I go into 4p, I have to include my d. So 3d, up, 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 down, 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 down. Now I can do 4p, 6, 4p, up, up, down, down, down. Now I can do 5s2. Okay, and this leads me to where I'm going to end, which is going to be 4d. Just to double check, I'm going to count to make sure. Yep, 4d9. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So we just leave one little blank space right there. Number 96. Oh, come on. Good. Number 96. Noble gas notation for the same three elements. So fluorine, with noble gas notation, you look at the previous noble gas and you just add whatever's left. So I'm going to take helium in brackets, and I'm going to add 2 helium, 2s2, 2p5. For calcium, the previous noble gas is argon, and I'm going to add 4s2. And for silver, Ag, my previous noble gas is krypton, Kr. And to krypton, I'm going to add 5s2, 4d9. It's 96. 97. What volume of carbon dioxide gas is released by the complete combustion of 59 grams of methane, Ch4? I could tell this is going to be what I call a grams in, grams out problem, but instead of giving you, looks like I give you grams in, but I don't ask for grams out, I ask for volume out. Oh, and I realized I forgot to give the conditions, so I think hopefully I'll remember to tell everyone, assume STP for this one, because without those conditions, you can't tell what volume that gas is going to occupy. You can find how many moles you're going to get, but you can't figure out the volume. All right, so we have to write out our balanced equation. Ch4 methane. When things combust, they react with O2 gas to form CO2 plus H2O. Now we need to balance. I always start with my hydrogens. 4 and this makes 2. Now if I put a 2 here, I always want to check evens and odds. If I put a 2 here, am I still going to have an even number of O's? Because I need an even number of O's because I only have O2. And the answer to that is yes. If I had an odd number here, I would double everything. But this looks good. Carbon, 1 carbon, 1 carbon. So we might be almost done at this point. Let's check our O's. O2 plus 2 more, so I think just a 2 there. And we're balanced. 1, 2, 1, 2. All right. So let's work out our equation now. I'm going to have to do a conversion here. So I need to get moles. 59 grams of CH4 times 1 mole over the molar mass of CH4. I'm going to cheat with my answer key here to save myself time. 13.04 grams. And that equals 4.5 moles. And That's moles of CH4. So 4.5 is going to go here. My X is going to go, I'm looking for CO2, right? So as you can see, it's a 1-to-1 ratio. So this is also going to equal 4.5 moles of CO2. Now, if we assume this is at STP, we can use our shortcut. We can say 4.5 moles times 22.4 liters per mole. We can get our answer. If it weren't at STP, I would have to tell you the T and P, and you would use the ideal gas law to find the volume. But for this case, we can just say this times that, which gives you 100.8 liters. And we need 2 sig figs here, so it's a little tricky. The only way to write this number with 2 sig figs is 1.0 times 10 to the second liters. That's my answer. 98. An 80.3 gram sample of water at 22 degrees Celsius releases 38,200 joules as it put in a freezer. What's the final temperature of the ice it forms? Okay, so this is going to be one of these heat problems. We have a cooling curve, 5 steps like that. I always mark my starting and ending points. So if I'm at 22 degrees Celsius, I'm right about here. And based on the phrasing of the question, it says, what will the final temperature of the ice be? I'm guessing we're going to end somewhere down here. So it's going to be a 3-part problem, and we're going to have to use several different formulas here. Okay? So part 1, we have to figure out how much of the 38,200 joules are released as it drops to 0. Then we have to figure out how many of the 38,200 joules are released as it freezes. Then whatever's left can be applied to cooling the temperature down. So really what we're solving for in the first 2 steps is Q. And that really confuses people because it gives you Q. I mean, Q says 38,200. But what we need to see is how much of that 38,200 is actually going to be used in these 2 steps. So step 1. Q equals MC delta T, and that's going to be MC2 delta T. I'm going to try to work from memory. I hope I don't get these constants wrong. So Q is going to equal 80.3 grams. C2 is 4.18 joules per gram degree Celsius. And delta T for step 1 is going to be 22 degrees because it goes from 22 to 0. Okay? You work this out and it comes out to 7,384 joules. I'm always going to leave my sig figs to the very end in this case. Step 2, we've brought the water down to freezing point, and now we need to actually freeze it. Formula for this, Q equals M times LF, latent heat of fusion. Your teacher might call that HF, just so you know. Q equals 80.3 grams times the latent heat of fusion of water, which is 334 joules per gram. Gram. And the answer you get is 26,820. Okay? What we're now going to do is see, well, how much of that original 38,200 joules is left. So I'm going to say 38,200 joules minus this gives me 3,996 joules left. That is my Q now. At this point, I'm trying to see, well, if I have this much heat left to give off, what is my change in temperature going to be? So I'm going to solve Q equals MC1 delta T. I'm going to solve this for delta T. Delta T is going to equal Q over MC1, which is going to equal 3,996 joules divided by 80.3 grams. And C1, I think it's 2.10, yes. Joules per gram degree Celsius. Check our units. Joule cancels joule, gram cancels gram, and degree Celsius is like that double denominator, inverse of an inverse. It's going to come up to the top. Final answer here, I get 24 degrees Celsius. That's delta T, change in temperature. And since we started at 0 and we're cooling down, my final answer, negative 24 degrees Celsius. Okay? On to number 99. Almost done here. Why does sugar C12H22O11 melt around 160 while salt NaCl melts around 800? It all has to do with the type of solid. Sugar is a covalent molecule, so it doesn't have any kind of strong bonds between neighboring molecules. There are, of course, IMFs, intermolecular forces. Now, I believe in the case of sugar, I would have to do a full Lewis structure to see if it is polar or nonpolar. I'm guessing there's some polarity to it, and that's why it's able to be solid at room temperature. Plus, the large mass allows the very strong London forces to keep it solid. But the short answer is, because sugar is a covalent molecule, it's a molecular solid, it doesn't have any real bonds between molecules. Whereas salt, NaCl, is an ionic compound, therefore NaCl is repeated over and over again in every direction, three-dimensional, and it all kind of latches together in that lattice. And because it's so strongly bonded, it's very strong, allows for that very high melting point, boiling point. Okay. Last question. This looks like an empirical molecular formula question. A compound was analyzed, and it had 9.8 grams of nitrogen. It had 0.70 grams of hydrogen, and it had 33.6 grams of oxygen. What is the empirical formula? So we're looking for like the simplest ratio of these elements here. So we have to find the mole ratio. Well, we need to convert all these to moles. So nitrogen, molar mass is 14.01, hydrogen 1.01, and oxygen 16.00. And when you work out the math, you get 0.70 moles of nitrogen, you get 0.69 moles of hydrogen, and you get 2.1 moles of oxygen. We look for the pattern here. Now I can clearly see 2.1, 0.7, and that's very close to 0.7. I'm seeing a 1 to 1 to 3 ratio. If you're not seeing that, that's fine. Pick the smallest one and divide each one into that, and you'll see it'll work out to about a 3 to 1 to 1 ratio. This is close enough for us to make a judgment call that that's the same mole ratio. So my formula is going to be 1N, 1H, and 3 O's. So based on our knowledge of acids, we're probably going to realize that this is going to be HNO3, nitric acid. Okay, and that does it for questions 1 through 100. Let me know if you have any questions in class.